Welcome to episode 6 of adding Houdini to your arsenal. Today I want to show you how to build the adding Houdini to your arsenal title graphic. This is a nice exercise in procedural modeling using volumes and for loops, two concepts we did not cover so far. So let's dive in and get started modeling this volumetric object. Let's get started by putting down a geonode. Let's call this volumetric onion skins, like so. And dive inside. Inside you will find the file sop. Get rid of it. Instead, lay down a box. By pressing P, you can show the parameters. Let's make this box a little smaller. 0.84 is what I found as a good value before. And now I want to squish the box in Y, so let's append a transform and scale it down in Y to 0.6, like so. Good. This box serves as a bounding box, basically, for the volume I want to use to scatter spheres or to clone spheres. So what I want is, I want to scatter points inside of the volume of this object and then put spheres on these points. To scatter points, I can use the scatter sop. But if I append the scatter sop directly, it will create the points on the surface of the object. And you will not find a parameter defining or specifying if the scatter sop should use the surface of the volume to put the points in. Instead, Houdini uses a very modular approach. So if you connect the surface to the scatter sop, the points are generated on the surface. If you use a volume, the scatter sop will happily create the points inside of the volume. So let's convert this box into a volume. That can be done using the ISO offset node. This is called ISO offset because it is meant to be used to create a shell around an object. To be able to do this shell operation, it needs a volume, so it's building a volume. But without changing this offset parameter here, we can just use it to create a volume from geometry. So connect this here to the very first input and make it visible, and you see instantly that you get a volume. By pressing D, you get the display parameters, and if you go to background, you can switch everything to dark, and that is beneficial with volumes because you see them better. What you have here is a fog volume. A volume is basically a 3D pixel image, meaning that you have little boxes here, and all these boxes can contain a value. And with a fog volume, these values are just floating point values. And if they are above 0, you see the fog. If they are 0, you don't see the fog. That is a fog volume. At the moment, the divisions of this volume are very low. If you middle click on the ISO offset, you see that you have 10 by 7 by 10 divisions, 700 voxels in total. And that is due to the uniform sampling division parameter. It tells that the longest axis here has 10 divisions. The height will have 7 divisions. To create more divisions, just up this number, say to 50. And you see that you get more definition here in this volume. And if you now connect the volume to the scatter, you see that the scatter no longer creates the points on the surface, but now inside of the volume. We don't want to scatter so many points, so instead of using 100 points, let's just scatter 15 here inside of the volume. In my example file, I used a global seed of 3, so let's do this to generate the exactly same result. And now we can create a sphere and use a copy to points and just copy this sphere on these points. Well, the sphere is huge. We can scale down the sphere, but another possibility we have that you learned last time is that we can use template point attributes. Let's do this. So create a VOP, point VOP, and let's call this set pscale. Remember that pscale is the default attribute that is understood by copy to points that defines the scale of the clones. Connect it here and dive inside. Let's make this viewport a little bit smaller, tidy this up a little bit, and now create a bind export and call this pscale because that is the attribute we want to set. For now, create a constant just to test if it's working, and connect it here. And as soon as you do that, everything vanishes, and that is because we are setting 0 as a p-scale value at the moment. If you up this value, you see now you can control the size of the individual spheres. If all the spheres have the same size, that is not very interesting. So instead, let's use an anti-aliased noise. So put down an anti-aliased noise node and connect P to the position. Now the anti-aliased noise function is sampled wherever a point exists. To be able to work with this noise, we want to first fit it. And that is due to the fact that anti-aliased noise is generating values between minus 0.5 and 0.5. You have to just remember this. So I want to have values between 0 and 1 because it's easier to work in this range. So I will fit between minus 0.5 and 0.5 and will transform this range to 0 to 1. What I can do now is I can lay down a ramp parameter, append it here, and instead of using a RGB color ramp that turns a float into a color, I use a spline ramp to be able to remap these values. And after that, I want to fit the whole thing again, because I don't want to necessarily use 0 and 1 as my final p-scale values. Instead, I want to be able to set the bounds manually. And to be able to do this one level up in the interface, I want to promote these two parameters, destination min and destination max. I can create a parameter node and connect it here, but instead there is an easier way. If you right-click on the port here, you can say promote parameter, then you get this little tick here, and at the same time the parameter appears in the interface of the WOP, and you can set it from here now. So if you do the same thing just to destination max, I have now control on the topmost level over what I am doing inside here. And I'll connect this to p-scale. Again, everything goes away, and that is because first we have this ramp defaulting to 0 everywhere. So if I go up here, you can see that I now have different sizes because they are using the noise. Now to design this a little bit, we can go inside and maybe up the frequency of this noise, or even change the offset. We can change these values, like so, or we can change the ramp to make the distribution a little bit steeper, for example, like so. That will do for now, but this is not totally interesting. So I want to put a second level of spheres on top of the surface of these spheres. So the first thing is lay down a merge that will merge different geometry streams and merge the original sphere and the clone spheres. The original sphere is too big, so create a transform here in the middle before merging that in. Now I have 3 inputs in this merge. That is due to the fact that the merge has a multi-input. And to get rid of this mess, I can use this list parameter here that lists all the inputs. And I want to get rid of the original sphere, so I can click on this little minus sign. And with this arrow, I can reorder the ports. And now this transform is going in first, and then comes the copied points. Now using the transform, I can make the sphere a little bit smaller, like so, and move it around by using the transform, like maybe so, just to make this distribution a little bit more interesting. Now I want to clone more spheres on the surface of this geometry. To be able to do that, I want polygon spheres, but at the moment I'm using primitive spheres. That can be told because of this wireframe here. So go to the sphere, SOP, and change this to polygon mesh. Now you have polygonal geometry. Now I can append a second scatter, this time scattering points on the surface of this geometry. And let's say we want to create 30 points here, and we want to copy, with copy to points, more spheres onto these points. So let's use this sphere again. Same problem as before. We have large spheres using the inherited p-scale value. So let's just copy our set p-scale and connect it here to give unique p-scale values to our small spheres and make these even smaller, like say so. If you now template the original geometry by using this pink flag here, you see now it's looking already a lot more interesting because we have large chunks of geometry and small ones. And to get everything in one geometry stream, we use another merge and just merge the original geometry that comes out of the first merge with the newly created copy to points, like so. And now I have this blob of spheres. And that will be used as a basis for my onion skins. So next I want to turn this into a volume, and this time into a signed distance field. But at the moment we have a problem, and that is self-intersection. So if you hover over the viewport, get rid of this template here, and press W, you see that the spheres are intersecting, and that is not good to create a volume. It would be great to remove everything that is inside of another sphere. And fortunately, there is a SOP that can do exactly this, and that is called the Boolean. So the Boolean in Houdini can not only be used to create Boolean operations between different geometries, but it can remove all self-intersections too. So if you feed this geometry into the Boolean, make the Boolean visible, then it will automatically get rid of all the self-intersections, as you can tell by watching the wireframe. And that is due to the fact that you have this Resolve Self-Intersections checkbox turned on by default. Now this geometry is watertight and has no self-intersections and can easily be turned into a volume. And we will use the ISO offset again to achieve this. So connect the Boolean to the ISO offset, makes the ISO offset visible. And at the moment you don't get much because we are still in wireframe mode. So press W again over the viewport and you see here is our fog volume. But this time we want to create a signed distance field. The difference between a fog volume and the signed distance field is a kind of value that is stored in the individual voxels. A fog volume, as I told you, stores float values, and a signed distance field does too, but it does store signed float values. And these float values have a meaning. They are the distance to the surface of the object. So if you have this surface here, let me template it, or let me make it visible. This surface here, and the signed distance field will store how far away a voxel is from the closest point on this surface. And that comes in handy to generate these onion skins later, because we can just use different ISO values to generate onion skins. So switch the output type from fog volume to signed distance field volume. And you get this because the resolution is too low. Now up the uniform sampling to say 200, and this will take a moment to calculate. And then you get this. You immediately see that you get artifacts, and that is because of the construction method of the SDF. By default, if you switch to this construction tab, laser scan is turned on, and laser scan speeds up the process and makes the construction faster, but a little bit more inaccurate. So tick this off. Will take some time to calculate, but the errors will be gone. And now you have a nice signed distance field. At the moment, the signed distance field is represented by the surface where the values inside of the volume are 0. So wherever the distance to the surface is 0, you see the surface. Now let's see how big our volume is. We can do that by using a node called volume slice. If you just append it, you get a polygonal slice that color codes the values of this volume. So here inside you see you have purple, and outside you have blue. And if I change this from -1 to 1, you can see where your values are. That is the distances. But at the same time, you see how big your volume is, because this slice is exactly the size of the volume. And you see that the volume uses the bounding box of the geometry. So it's as big as it has to be to include all the geometry. But we want to have it bigger, because later on we want to extend the onion skins outside. So we need a bigger volume. How can we do that? Well, we can use a geometry with the second port of the ISO offset to tell the ISO offset how big the volume should be. And how can we generate such a geometry? By using the bounce sub. So if you use the original geometry and put it inside of a bounce sub, you get a box that just includes all the geometry, as you can see here. But now you have this lower and upper padding values, and these can be used to make this box larger. So if I put 0.5 here, everywhere but on the Y, I get a larger box. And now I can connect this to the second port of the ISO offset, and still the volume is not bigger. But as soon as we go to ISO offset and back to the dimensions tab and now say override bounds, it starts to immediately recalculate the SDF, and you see that we now have a volume that has values wherever this bound geometry is present. So we fill the space outside of our spheres with values too. Now that we have this volume, we can convert it back to polygons and thus create these shells. To do this, we use a convert volume node, this here, and connect it to the volume, make it visible, and it generates a polygonal surface from the volume. But the good thing is that I now have this ISO value control. And if I change the ISO value, you see that I can generate a different surface, a dilated surface, so to speak. And that is the case because this surface is the surface where, inside of the volume, the values in the voxel is 0.168. So everywhere where you see this surface, this value is present. And that makes sense because the values inside of the volume are the distances to the original surface. So here, the distance to the original surface is always the same, and so we can generate this shell. And it works in the other direction too, minus. So we can erode the thing, so to speak, and go inside. So this is very flexible because with this ISO value we can decide where our surface should be inside of the volume, as you can see here. And because the volume is big enough, because we made it bigger using the bounds sub, we can generate hulls that are quite a bit apart from the original surface. To create the graphic we have in mind, we not only need one of these shells, but we need many. And of course, we can just duplicate these convert volumes or create many of these convert volume nodes and use different ISO values to generate different shells and then merge everything together. But that is cumbersome. So instead of doing it manually, let's use a for loop. A for loop can be used to iterate over certain nodes inside of your network. So to re-cook some nodes more than once. And it can be invoked by laying down a for loop with feedback. If you do this, you get these two nodes that are encapsulated by this convex hull in the same color. And everything that goes between these two nodes, the repeat begin and the repeat end, will be executed more than once. If you select the repeat end, you see here the iterations parameter. And that tells how often this loop will execute. So just to give you an example, if I create a null and feed it here into the loop, at the end we have nothing because a null stays a null. But if I now create a merge here inside of the loop, I can merge geometry inside of the loop. And if I now create, say, a sphere, like so. Remember, this sphere is a primitive sphere represented by 1 point, and if I now feed it into the merge, I have, after the execution of the loop, a sphere here. It looks as if it is just one sphere, but a middle click tells us that it is 10 spheres. So we have 10 points in this geometry stream now. And that is because this merge here is executed 10 times. We created a for loop with feedback, and that means that after each iteration, whatever comes out of this port here is automatically fed into the loop again. So the very first iteration uses a null, but the next iteration uses the output from this merge operation. And thus, these spheres add up, and in the end, we have 10 spheres. But of course, we cannot only do this with spheres, but we can do it with our converted volume. So if you feed this in, you get a lot of points. One of these shells has around 55,000 points, and after the operation we have 500,000 points. So after the loop we have 10 shells packed on top of each other. And now to generate different shells, we have to vary this ISO value with every iteration. That is our goal. If we can vary this with the iterations, we will have different surfaces, and all these surfaces will get merged together inside of the loop, and in the end we have a lot of individual slices of this volume. So how can we set different values here? Well, the very first thing is that we need the iteration count, or the iteration number. We need a number that tells us which iteration is currently processed. This number goes from 0 to 9, because we have 10 iterations. So the very first iteration has number 0, the next one 1, 2, 3, and so forth until 9. And if we would have such a number, we can use it, using an expression, to set this value based on this number. Of course, we don't want to put 0, 1, 2, 3 here, because these values would be too large. We need values that go somewhere between 0, let me make this visible again, otherwise the loop executes all the time, between 0 and, say, 0.5. So we somehow have to transform this iteration value to a range of 0 to 0.5. But first we need the value. And the good thing is that we can get this value. It's a little bit complicated, but bear with me, it's doable. This repeat begin node is in charge of feeding the result into the loop again. But if you select it, you get this button here saying create meta import node. If you press the button, you get a second input node. Looks similar to the first one, but it's a very different kind of input node, because this node here is set to fetch feedback. That means it fetches the feedback from the output node. But this node here is set to fetch metadata. And what that means is that it will add detail attributes to itself. Detail attributes containing information about the loop. I told you in the episode that talks about attributes that there are different kinds of attributes in Houdini: point attributes, primitive attributes, and detail attributes. Detail attributes can be set once per geometry stream, and that is why this node is setting detail attributes, because we only have one iteration value for the entire geometry here, not one per point or per primitive. If you go to the geometry spreadsheet, have this node selected, and then go to detail, you see these 4 attributes are added by the node: the iteration, the I value, the num iterations, and the value. The iteration is the current iteration. At the moment it's set to 9 because the whole loop executed. So it counts up, and after the last iteration it's 9. And the num iterations tells you how many iterations there are in total. And these 2 values are of interest, because with these 2 values we will be able to map the range from 0 to 9 to a range that is more suitable to what we need here in the ISO value. So how can we map these values? There are different possibilities. We could use HScript, but we can use Vex too. And I prefer Vex because it's faster and it's nicer and you should learn Vex. So let's just write a little Vex to generate the right values to use them later here in the ISO value. The easiest way to introduce Vex into your scene is to use a wrangle node. So create a point wrangle. A point wrangle allows you to put Vex code directly here in this Vexpression field. And this Vex code is then directly executed. It's the Vex counterpart of the point VOP. And in reality, it is a point VOP. Houdini uses digital assets, that is, packed nodes, and this point wrangle here is one of them. You can tell this because it has this little lock icon. If you right-click on the node and say Allow Editing of Contents, this lock opens and you can double-click to dive inside. And you see inside you just have a VOP. And in this VOP you just have one node, a snippet node. And a snippet node is a VOP node that you don't know yet that allows you to implement a custom node using Vex code. So what a wrangle really is just a VOP network using a snippet node. But it serves as a way of writing Vex directly. This is just a standard Houdini node, and now that we want to implement a mapping of the values, the very first thing that we need is the I value that is generated by this repeat begin. How can we transfer this value here to the Vex node? The Vex node is living here outside of the loop, and we have to insert it before the convert volume. So let's do this quickly. Here before the convert volume, because we want to generate the values before the convert volume to be able to use them later on in the convert volume. So to get the detail value here, we can use a parameter. And there are different ways to generate a parameter in Vex. The easiest one is using a channel function. So inside of the Vex code, let's first define a variable. The variable is of type float. In Vex you have to explicitly state that. So type float and then num_iter, which is the number of iterations. And then you can invoke a function. And this function is called channel and is abbreviated with ch and then brackets. And at the end of each line in Vex, you use a semicolon to tell the Vex compiler that the statement ends here. And now we want to give our channel a name. Let's call it num iterations, like so. So now what happens here is that you define a variable, so a named space in memory where you want to write a value, the value that this channel function gets from a parameter. But at the moment there is no parameter. You can create one using this edit parameter interface menu item, or in wrangles you can just press this button. And if you do that, the code is parsed, and if it finds a channel that is needed, it automatically creates one. And that is the case here. Now we have a num_iterations interface element. And whatever I put in here will be saved to this variable num_iter. At the moment I have 0 here, but what I really want to have here is the num_iterations value. And to read it from this node here, we have to use an hscript expression to read the detail attribute from this node and put it here into this field. And then it will be transferred to the Vex code and saved in this variable. The function we want to use is the detail function. To be able to write an expression here, you can just start to type, or you can hover over the field and press Alt-E to open the expression editor. That way it's easier to see what you are writing. The expression we want to use is called detail, and it has a certain syntax to it. The first thing that you have to put here is the path to the node that you want to use. The easiest way to get a path to a node is to use the Python console, the Python shell. Here under Window, you can open the Python shell, and if you now drag a node into this Python shell, it gives you the direct path to this node. That is the easiest way to find the global path to a node. And you can just copy it here and use it here inside of your detail function as the very first parameter, like so. Then next, you want to use the name of the attribute you want to read. Here, under usage, you get a hint how the expression is structured. So the very first thing that you have to put is a surface node, and then comes the attribute name. And the attribute name is numIterations, like so. And last but not least, you have to specify the field, because numIterations is just a float, but it could be that this attribute here is a vector or some other type of attribute that has more components. So you have to specify which component you want to read. In our case, this is just 0 because it's the very first component. And keep in mind that this is HScript, so we don't need a semicolon. Press apply and accept. And now you see the numIterations parameter is read from the detail attribute and put here into numIterations. And at the same time, we have the number of iterations inside of this numIter variable inside of vex now. Now let's do the exact same thing for the next value we need, which is the current iteration value. So write another float variable, call it ival, and use another channel function, this time calling it ival, like so. If you again press this button, a new field will appear called ival. And now I can just copy all of this here and put it here under ival. If you press Alt-E, the expression editor opens, and this time we don't want to read numIterations, but let's quickly look it up. We want to read iValue. So change the name of the attribute from numIterations to iValue. Press apply and accept. And now you have the iValue here. So now I have the numIterations and the iValue. That enables me to generate a new mapped value. What we want to do now is use the fit function that we know from VOPs, but its vex counterpart, so the fit function itself. We first generate a new variable. Let's call it isoValue, because that is the value we want to generate. And that will be generated using the two variables that we defined. So let's create a fit function. You can use the help and go to vex functions to look up all the vex functions that you have. And if you put fit here, you find the fit function. If you click on it, you see the syntax that is needed. So the fit function takes in a float value, and then it has 4 other values: omin, omax, nmin, and nmax. That means old minimum, old maximum, new minimum, and new maximum. This is analogous to what you find as an interface on the fit node inside of VOPs. It's exactly the same thing, it's just that you state the values by text, one after the next. So let's just copy all of this stuff here and return to Houdini and just paste it here. And again, press Alt-E, that is possible for vex too, to open up this expression editor. That is easier. So these float values here are not needed because they are just in the help to tell that this is a float value. But instead of using this, you can use the values directly here. So replace all of these strings here with the current values that we want to use. So what do we want to fit? We want to fit the I value. The I value is the input. And the I value at the moment lives between 0 and the old max is the numIterations. And we want to fit it to new values. And these values should be around 0, not too far away, because these are the real world values that we intend to use later on. So let's say it should start at minus 0.1 and go up to 0.2. We can change these values later. And don't forget to terminate your statement with a semicolon. Now I created a new variable isoval that calculates a new value from the two values that we read into the node. And now it's just about using this value. We somehow want to transfer this value down to the convert volume, and we again use a detail attribute as an interface. So let's use a function called setDetailAttribute, setDetailAttrib, brackets and semicolon. You see if you typed a function correctly as soon as it turns blue, and this is the case here. And now we can look it up. setDetailAttrib. And you see that you first have to specify the geohandle, so the geometry that it's operating on. Then you have to give your new attribute name, and then you state the value. And last but not least, you have to tell it to set the parameter, because you can, in theory, add to an already existing parameter or multiply or other operations. But normally, what you want to do is to set the value. So let's switch to Houdini and use that. The very first thing is that we want to operate on geometry stream 0. Then we want to tell the function the name of the attribute to set. I call it isoval. Next is the actual value that we want to write to the attribute, which is isoval. And don't get confused here. This isoval here is referring to this variable inside of vex. And this isoval is a string that gives the name of the attribute to be created. And then don't forget to pass a string that is called set to tell the function to set the value. And now press apply and accept. And if we did everything correctly, now you get an isovalue detail attribute here on the point wrangle. And at the moment it's 0.2 because the whole loop executed and all the values are at their maximum. But the node generates different values for all the individual iterations, because these two values here will change for every iteration, and thus the ISO value will change for every iteration. So the very last thing we want to do is to use another detail function to read this detail attribute into this ISO value field. So go to the convert volume and press Alt-E here in the ISO value field. Now again, quickly open the Python shell and drag our point wrangle to the Python shell. And you get a new path, and this path is obj volumetric onion skins point wrangle 1. Copy it and use a detail function here. Remember, first we have to specify the path to the node we want to use. Then we want to tell the function isoval the name of the attribute to read, and then the field, which is 0 in this case. Press apply and accept. And now we have this ISO value here. And if we now switch to scene view and go to the end of the loop, we have to wait for a second to make it execute, and you see now it is working. Because what happens now is that this vex code here is executed for every iteration. The ival will change with every iteration, and thus the computed isoval will change with every iteration. And this ISO field here will read the computed values from the point wrangle through the use of a detail attribute and will be different in every iteration. So this convert volume creates different geometry with every iteration, and all these geometries get merged. And after the loop, we have 10 shells here of our object. And of course, you can go in and change these numbers here. So if I go from minus 0.1 to 0.1, you see that I have now smaller gaps between the individual shells. If I go from 0 to 0.3, say, I can generate values, or I can generate shells outside of my original mesh. And that is the basis of how the title graphic of adding Houdini to your arsenal is generated. Now that we have this basic thing, it's about tidying it up, giving it some nice colors, and rendering it. And I will talk about these things in the next episode. So thank you very much for listening. I hope you learned a bunch. It was quite a mouthful this time with all these loops and wrangles and backs, but I think it's very handy knowledge to start to build your own procedural modeling setups. Thanks again, and see you.